Hello, in this video we'll cover two questions. So that will be 2.50 and 2.51. Both of these questions would involve the equations of conservation of momentum and probably this equation as well. So pause the video, try it yourself, and we'll go through it together.
A few moments later.
Okay, for the first question, the question told us that there are two masses. So the first one, let's call it M1. The other one, let's call it M2. And M2 actually has twice of the mass of the first one. So let's call it 2M. M1 is moving, so U1, the second mass was stationary, so U2 equal to 0. And after the collision, they will stick with each other. So you may write down V1 equals to V2 equals to common velocity Vc. And I think this is what I'm trying to demonstrate to you, that you can always write down the things so that you can kind of translate the wordings into a mathematical relationship, and that will be very useful if you want to get a smoother workflow. And the question asks you to calculate the fraction of the original KE. So let's just call it KD1 that is lost. I think there's a wording missing. I think it means 2, that is 2 lost. And I suppose that is I think the one that I actually don't know. I guess what they are trying to calculate is KE delta KE, so that is the KE1 minus KE2, or the other way around, it doesn't really, there's a negative, over the original KE. I think that's what they are trying to find. So before we find the KE cost, we will need the expression for velocity, so we will have to do another equation that is conservation of momentum first, obviously. So let me just write down the equation. In fact, before you write this down, you should always double check the assumption. And for this equation, the assumption is there's no external force acting on these two objects during the collision. And yeah, of course, this is true. And so this is how you can use this equation. So after you get this equation, you can just substitute what you know from the condition. So M1 is just M, and then U1 I'll just keep it as U1. Then U2, since it's 0, then no matter what you multiply, is 0. M1 and M2 all together is actually, you can put, well, I wanted to put 3M, but then let's just put M plus 2M bracket Vc. Okay, and then I hope you can see that the M will cancel out, so you only have U1 equals to 3 Vc. So this is the relationship you can derive for now. So back to the fraction, I think we can find out the expression by saying half the final one. Okay, so well, I suppose this is the KE2 minus KE1 over KE1. So that should be half M, so I can just treat it as one single object, so 3M V squared, so Vc squared minus the original. So the original is just the first object, which is half M V squared, so U1 squared. Okay, so this is the KE1, which is the same at the below of the fraction. U1 squared. Okay, and the good thing is you can firstly see all the half 1 over 2, and the M will cancel out. So let's just simplify for that part first. So you can have 3 Vc squared minus U1 squared, right? And then U1 squared here. Okay, and then this is a time where you apply the relationship that you can find from conservation of momentum. So probably I will just substitute U1 as 3 Vc. So 3 Vc squared minus this is square, so that will be 3 VC bracket square, so it will become 9 VC. So if you are okay with this, then I will just write it directly, 9 VC square, same as below. So eventually you get all the VC square cancel out, and then you only have negative 6 over 9. So that will be, if you want to find the fraction, that I suppose we will express it as 2 over 3. So that means for the change of percentage change or fractional change of the kinetic energy, you kind of lose 67% of it. By the way, if you go back and look at the requirements of the IB physics syllabus, the idea of elastic collision and inelastic collision are written there. So this is something that we haven't mentioned by now. So this is I think, a good time for me to talk about it quickly. Alright, so maybe I'll just write here, for both of these collision, for the momentum, it will always conserve. So you can always draw a table like this to help you to understand. So elastic and inelastic collision, both momentum would conserve. Alright, or I put a tick simply. So same for inelastic. Again, the only case when you don't have the momentum conserve is there's external force, then momentum won't conserve. However, for energy, for elastic collision is simply by definition. Okay, remember, by definition, there's nothing we can deduce or derive from it. Then it would conserve for elastic, while for inelastic, it would not conserve. So that is to say, just now in the previous example, whenever you got one mass colliding with another, and after that they both move with a common velocity, you can actually can tell in general all these situations whenever they have a common velocity would be the case of inelastic collision. Let's try the next question. So it said there is a body that is at rest, so U equals to 0 of mass m that explode into two pieces. So this is, you may find, oh, what kind of question is this? This is actually one kind of conservation of momentum question, because probably here we are talking about in the space, so there's no other force that will be relevant, no air resistance, no gravity as well. So when you explode, that will be the internal force that push each other apart. So two masses, m over 4 and 3m over 4, which you can see add together will just be m, so there's nothing else, just these two. Calculate the ratio of the kinetic energies of the two fragments. So I suppose I have to write down the Ke of the m over 4 and then the Ke of the 3m over 4. So normally, if you try to use the usual kinetic energy equation, which is half mv squared, it is fine. You could also use the equation that is you have proven here. Okay, so I'll give it a try to use this equation. Actually, I don't use this often. So p squared over 2m. Maybe I'll just write here, kinetic energy equals to p squared over 2m to remind myself. And so in this case, that would mean I will have the momentum of m over 4 squared over 2m, which is m over 4, times the, you know when you divide something, you flip the fraction. So that will be 2 times 3m over 4 of the momentum of the bigger one, 3m over 4 squared. Okay, but then you need to find the expression for the momentum, of course. So once again, you need to go and think about from the conservation of momentum perspective. And that is to say, once again, you have mu, well actually it's just 0. right? So mv plus mv 1 1, or you can, well, let's just call it 1 and 2. 1 and 2 is just easy. I don't bother to write that many times. All right, and this is just 0. These are just 0. So 0 equals to m over 4 v1 plus 3m over 4 v2. So if you try to rearrange the equation and also cancel out the m and also over 4, you have probably negative v1 equals to 3v2, alright, which correspond to the 2 momentum here. Oh wait, I don't have to do this because there's no momentum, and so when they split, because whenever they split, they must go in the opposite direction, right, to keep the whole momentum conserved. And so the momentum of these P would be, of course, opposite to the other one, negative P, because again, conservation momentum, right? You don't even need to calculate this at all. All right, I'm showing a very bad demonstration. So in fact, this one and this one will simply be the same magnitude, it's just opposite, but then there's a square here, so you don't have to care about this negative anymore. So these will just cancel out, okay, and then 2 will get cancelled out, 4 will just cancel out, and then 3 over m will got cancelled as well. Let me just write down here, 4 cancel, m cancel, oh, everything is done. So, well, then the answer is simply 3 then. Oh, this is, yeah, how you can do it easily.